Good morning, developers. If you are new to the channel, my name is Rob, and it is CS Thursday. We push our keyboards off to the side, usually, and try and figure out how things work on Thursday. Computer architecture, programming languages, that kind of thing. And today I want to test this question. Is JavaScript insane? Depending on where you're coming from, this might mean nothing to you, and you're thinking, Rob, what are you talking about? JavaScript's just fine. I program in it every day. If you're coming from another language or if you've been doing it a long time, it probably has some meaning because JavaScript operates in very, very strange ways at times. And I'm talking specifically with regard to the model, to the paradigm that JavaScript uses, the event loop, the asynchronicity, the concurrency, that kind of thing. A lot of these videos are born out of other videos I've done, and I've been talking about promises lately, some of the updates to JavaScript, and it all kind of mixes together to where it's like, okay, let's talk about this, because this is one of those things that really commonly gets skipped over among JavaScript developers. So many of us are self-taught. You didn't go to a computer science program. You didn't go through a really rigid, hey, this is how everything works, right? How the stack, the heap, and the queue work, and this is what the runtime model is. You just started coding it, and it worked, and you got a job, and you got better, and you got better. Coming back to this and understanding how things are working under the hood, I think makes all the difference, because it goes from JavaScript's insane, it's ridiculous, it's not being fair, it's running lines totally out of order, to, oh, okay, I understand, this is perfectly sensible. And I can say with a totally straight face, is JavaScript insane? JavaScript is an incredibly brilliant model. The paradigm is different, but it is brilliant. And it blows my mind to think that in 1995, Brennan Eich made it in 10 days. And here we are, almost 30 years later, depending on when you're watching this video, JavaScript is not, the paradigm has hardly changed. Yes, there've been updates over the years, but to go from a web that was dozens of pages, maybe 100 web pages, to where there are literally billions, tens of billions of sites, and we're using JavaScript on the back end now with Node.js. There are large frameworks with thousands of people managing them. For JavaScript, for the paradigm to remain relevant, not just relevant, but effective, is mind-blowing. So, is it insane? I'm going to tell you up front, it's not. It's incredibly awesome and very, very consistent, but it's different than C, which is kind of the paradigm for most modern languages, and I would say in two basic ways. But let's start here first. Let me grab a different color, actually. If I write this up here, if I said let count equals 0, is that JavaScript? Okay, pretty leading question. The answer is yes. That's obviously valid JavaScript. You, as a JavaScript person, can read that and know what that is supposed to do. But if I put that in a file and label the file .js, right, scripts.js or something, has it become JavaScript? Well, no. So take a step back. What this really is just some English, right, that follows some rules. That's all a programming language really is some syntax and semantics. We just agree as JavaScript or ECMAScript, however you want to prefer, right? The rules, we follow them, and that's what makes JavaScript a programming language. This has to be processed. It has to be converted into something else that a machine can understand, namely a bunch of binary data, or ones and zeros, or ons and offs. And I've got other videos on how compilers and interpreters work, and I can link those if you want to run down that road. But getting from this to actually some machine code, we've got to go through what is called a JavaScript runtime. And that is the thing where the magic happens. Magic happens everywhere in this process. But the JavaScript runtimes, I'll label a few here. Actually, let's stick with, let's use orange. Typically, you are going to be running JavaScript in one of two places, in the browser or in Node.js. And with the browser, you've got an option of, say, Firefox, Chrome, Safari, Edge, etc. Okay, there's a bunch of different options. Like I said, you could also be running this on the back end in the form of Node.js. This line here would make sense to a runtime in any of these places. Now, all of these places, the runtimes, okay, that are implementing this runtime model, the event loop, they all have their own engines. So Firefox uses what is called SpiderMonkey. Chrome uses V8. Node.js uses V8. Internet Explorer, Edge, that whole family, I think it's still Chakra. I don't know, Edge may have moved to some version of V8, but the point is they all have their own engine. And the engine meaning this is the thing that's going to take this stuff in green, let count equal 0, and get it into machine code. That process means they're following the rules and they're expecting us to too. It's not any different than right now I'm speaking English. As I speak English, I'm following the rules, and I'm expecting that you understand the rules so that you can actually make sense out of what I say. If you don't, then as I speak, all you're going to be hearing is a bunch of sound waves that mean nothing. Or as I'm writing up here, you're just going to be seeing a bunch of squiggles that also mean nothing. There are some slight nuances. So if you're in Texas, or you're in East London, or you're in southern India and someone's speaking English in any of those places, it might vary slightly. Everyone's following the rules that they have established. And that's the same thing here. We've got a bunch of different JavaScript engines. Firefox treats, right, with SpiderMonkey, I guess I should say, which is the engine on Firefox, it maybe implements quicksort. So you run .sort, and it's going to do its own version, right? It's going to implement it a specific way. And Chrome with V8, maybe .sort actually does merge sort. Okay, so there's some small nuances, but the model, the basic, the structure is always going to be the same. Otherwise, it's not JavaScript. Otherwise, it's not English. Okay, so that's thing one, is that we have a bunch of engines. And the engines, their job is to take our code, right? Our English, if you code in Hindi or Mandarin or German or whatever, take your code and process it this way, the same way every time, so we as developers can get the same results in our applications. Okay, the other thing to note up front here is that JavaScript, unlike almost all languages, is single-threaded. Python is single-threaded as well, but you can get to a kind of a multi-threaded paradigm with a library. In JavaScript, I do not know of any way to ever simulate a multi-threaded approach. What does this mean? Single-threaded means JavaScript can do one thing at a time. No exceptions. It can never do more than one thing at a time. So everything we're looking at here, when your runtime, okay, so when your browser or your Node app, maybe you're using Unity. Unity has a flavor of JavaScript. Whatever engine it is going to go to the operating system, right? Say, hey, I need a thread. I need to do some stuff. Okay, the processor needs to give me one of its threads. It grabs that thread, and that is it. There are no more threads that JavaScript is capable of operating. Everything happens here on one process. Now, this is really powerful for a bunch of reasons. And again, I think that the model is brilliant. But something like C, on the other hand, or again, Java, C#, it can ask, the runtime can ask for a thread to start doing something. If it wants to do something at exactly the same time, it can ask for another thread. And so you can have two different things happening at the same time. That's really powerful because you can do multiple things at a time. It's also really dangerous because you might have two threads that are trying to run the same code or do an operation and modify or manipulate data at the same time, and the program can lock up. So there's good things and bad things about both. JavaScript, though, is single-threaded, so everything that we're about to talk about here, as implemented by the JavaScript engines, the JavaScript runtimes, it is one process, and it can only do one thing at a time. It can never do more than one thing at a time. So how do we process the code that we write? What is the process that it goes through on this one thread? Okay, this diagram here. Let me pull it up on the web quick. I pulled this almost exactly from the MDN doc. So if you go to this URL, you can search for this title as well. You should get this diagram if you want to go back through and break things down. We're going to use this diagram to try and understand the process that it goes through as it runs lines. But there's only so much I can do that makes any sense here when I'm drawing on the board. So we're going to hop back and forth between a coding window to try and make sense here. Okay, this is the model. This is how JavaScript engines run your code when it actually looks through line at a time and what it does. These are some scary terms. I totally get it. I avoided them for years because I didn't want to think about it. I was like, hey, I can write code and I don't need to know any of this. JavaScript handles it under the hood. Yes, but my life was so much more miserable at times because I didn't take the time to understand how it works. All right? First thing, we have something called the stack. The stack has its own memory allocation. So when the engine runs, it will go to the operating system and say, hey, I need some memory. I need my own memory for the stack. The heap does the same thing. They are completely separate chunks of memory. The heap says I need, or the engine says, I need some memory reserved for the heap. Okay? The queue, it works a little bit differently. Don't worry about that just yet. What is the stack? Okay, the stack contains frames. What is a frame? Well, when we run our program, if let's say we have a file called scripts.js, and this is the only thing that we have inside there. We literally have let count equals 0. We don't print anything to the screen. That's the only thing we have, and we run it. We open it up in the browser in Node.js, something like that. What really happens is this. JavaScript is going to write its own function. It's an anonymous function, but to make it a little more sense, I'll just call it main. And it will take that line and drop it in there. Let count equals 0. And it will run that function. So this is what's going to happen under the hood. Even though we only have one line, there is a main function that is going to run that's going to wrap around everything. Okay? As our code runs, so this is the very first thing to try and keep in mind. When JavaScript starts, it starts at the top of whatever the entry point is for our application. It grabs the very first function. If you don't have one, it will make one. And it puts that as a frame on the stack. Okay? A frame is a function, and a frame contains a few things. They all contain this stuff. A frame is going to contain, I'm going to put it over here. Let's do it here actually. A frame is going to have its own scope, meaning its own variables. So as I mentioned, the stack has its own memory. Whatever frame is running right now, it's going to have its own variables internal to that function. Even if it's at the global scope, right, it's still going to get put inside of a function. That's that frame. Count equals 0. This is a variable that needs to be stored in memory somewhere, so it has its own scope. It also has its own arguments, so whatever things were passed in this case, we wouldn't have any, but it would maintain arguments if they existed. It has its lexical scope, meaning what do I know that's above me? So not specifically my stuff, but of whoever called me, I have access to those variables, right? Because child functions always have access to parent function variables. And then lastly, it's going to have some notion of what this is, okay? The frame, every frame is going to have that stuff. And the frame is a function that gets put onto the stack, okay? So far so good, I hope. We've got a dirt simple program. We've got one line, let count equals 0. This is going to get put in a function, and this function is going to get when the runtime, the engine here in orange, when that executes our code and converts it into machine code, it's going to take this, create a frame, put it on the stack, and it's going to have its own scope argument, lexical scope, and then it's going to have its own this. All right? If things get a little more complicated to where inside here, we call our own function. So in addition to let count equals 0, let's say we had something like we called func1, open close. That means inside this frame, we call another function, which means that code is also going to get dropped on the stack as a new frame. So we haven't defined this func1, but it would have its own scope, its own arguments, its own lexical scope, and its own this. And the stack is going to get built that way. As functions get called, they will get added on top of the stack, all with their own stuff. The stack is processed from top to bottom. So it's a LIFO model. I'll go ahead and put that up here. LIFO means last in, first out. So the most recent frame added, the most recent function run, is what's going to get put on the top of the stack, and that's going to get run first, and it's going to work its way back down. This makes perfect sense. If you have your global function and you call function one has to finish before we can continue on through the rest of the parent function, right? That's what's happening is this frame gets put on, it calls something, this frame gets put on, we have to finish this one before we can come back to this one. Last in, first out. Stuff gets put on the stack in that order. If my func happened to call a frame or a function, we would end up with another frame. And so on. As frames get added and then they are completed, so the function finishes its code, it will return, even if you don't return something, it will return null. That frame gets popped off the stack, and all of this stuff that's no longer necessary, no longer going to be used anywhere, gets removed, and it goes back down to the next frame. Okay? So that's thing one. Your code, as it's run by JavaScript, is organized in the concept of functions or callbacks, which we haven't talked about yet. And those functions are going to get put onto the stack. They're going to get stacked on top of each other, and they're going to get processed from the top down until eventually there's nothing left. Okay? As a quick note here, if you end up with too many frames, too many function calls, that is known as a stack overflow, because you have added too many frames to the stack so that you have outrun what memory has been allocated to it. So Firefox told the operating system, hey, I need this much memory. You keep adding frames because you have a recursive function call, or you have an infinite loop, or whatever, and too much stuff gets added, it runs out of memory. That is a stack overflow. That's why it's called that, is because the stack here is where things are processed. One more thing to note here, and then we'll look at how the queue gets involved. The stack operates synchronously, so it's going to take the last in first out. The JavaScript is going to be operating on the thing at the top of the stack, and it is going to run every line synchronously from top to bottom, no exceptions. Okay. You're thinking, wait a minute, Rob, there are exceptions. It doesn't always run every line in order. That's because some of those lines are functions or callbacks. So as the code is running, if it ever has to wait, if JavaScript ever has to wait for any reason on a particular line, it will register that function, that callback, whatever you want to call it, and it will move on to the next synchronous line that it is able to run. So we're in the stack, we've got a frame, it will run every line in order until it gets finished, and then it can pop the frame off the stack. If it runs into a function, right, a callback, so something in there like a click listener or a fetch, go out to this API and go find some data or whatever. If that happens, it's gonna put that on the queue as a message, and a message is essentially a callback. So this is some code, this is a function that needs to run that I can't wait for it. I'm single threaded. I go straight through. I run the code in order, and if you give me a function that's not being called right now, but you let me know, hey, this function runs when this happens, this someone clicks on it, or the fetch API is back, or I'm writing to disk, or I'm making a database insert, something like that. I'm gonna put that here. And then I'm going to keep doing my thing here. Okay, when will this run? Well, whenever the stack is empty, all of these frames have been finished, then it will come down to the queue and it will grab these. The queue is FIFO, meaning first in, first out. So it will operate what is the oldest thing in the queue that has been waiting in the event loop. So we process this stuff. When this stuff is done, then we go down to the queue and see what's in there. Has anything happened? Okay. Oh, a click happened a few milliseconds ago, and I'm done with all my synchronous code here. I've done everything. I can grab this. What does it do with that? It will take this and it will move it to the stack. It will move that callback up onto the stack and process it exactly the same way as we've been talking, where it will run each line in order. If it runs into any callbacks, any functions that will need to be run later, it will drop them onto the queue. Again, it's called another message. and it is FIFO, and this will sit here until the stack is empty, and then it will get moved in. Every single time JavaScript encounters one of those, this is going to get thrown onto the queue, and the queue is processed. The event queue, or the event loop, is going to constantly be checking the queue once the stack is empty to see, can I do anything over there? Oh, I can. Let me go grab it. Okay? Let's do a quick actual code example will help make it make sense. Over to a more familiar scene, let's add some concrete to our abstract. Get away from the board and actually look at an example so you can see, we could talk through how the stack works. And I've already got a few files put together here so we don't have to code them out. They're just going to be examples. And I am going to use Node.js instead of the browser. If you want to follow along, make some HTML files with script tags if you're more comfortable there. What we've got is similar to what I had on the board. We just have one line. It's not in a function. There's nothing to this. If I come over to Node and I run it, it does exactly what it's supposed to. There's no magic here. The reason I show this example is because this is what really happened. This cannot run in a JavaScript runtime by itself. Only synchronous code running on the stack does. So what JavaScript did was this. It added a self-invoking function like so. Now we've got something to put on the stack. This function is put on the stack. It's code. It comes with all the, it's a frame. It comes with all the stuff that comes on in a frame. It ran line 3. It was out of code. There was nothing left to do, so it got popped off of the stack and the program terminated because there was nothing else to do. Okay? That's the only reason I show that is so that you know, again, everything runs from the stack, no exceptions. I'm going to drop in another example here and we'll talk through it. This is just like the last one. I just don't have that self-invoking function in there. You could put it in if you want to. I'm going to leave it out just so that you know this is inside of a function that gets added to the stack as a frame. The code runs synchronously. How so? Well, set timeout gets added. This callback right here is part of the set timeout. And the way that actually works in JavaScript, the engine doesn't add this to the queue until this is done. That's actually the browser's job. So the web API, which is part of the runtime, not strictly speaking the engine, it's not super important for this video, but this callback isn't going to get added to the queue until the timer is up. The timer's up, so it's going to get thrown into the queue. Will this be run immediately? We'll find out. Humor me if you already know. Line 5, we have the set timer was added. So this is the third console.log. We've got these two that are supposed to run in 0 seconds, and then we've got this. I grabbed the time so that we can see how long this takes to run. And then I've got a loop that runs 100 million times. It looks like I got a mistake down there, but we're going to run from 0 to 100 million, and then there's just a little logic here. If I is divisible by 10 million, then just print off where we're at and that it's coming from the stack. This is synchronous code, so this will definitely run in order. It's just how will it run with relative to this stuff up here. Lastly, line 14, we get our console.log, okay? Where and when does all this stuff happen? I'm going to come over, I'm going to run our code again, and the first thing that happens is set timer added. So that means line 5 is the first log that we get. So even though this was going to wait 0 milliseconds, where do callbacks go? According to our whiteboarding session there, they are put on the queue. They are not executed first. The stuff on the stack is executed first. So we can put a note in here. Global function is wrapped around everything and it is added to the stack. Inside here, this callback is added to the queue, and I'm going to put messages here because that's what the web speak is. Queue messages are only added to the stack when the stack is empty. So this thing, even though the time is up, it's sitting in the queue waiting for the stack to be empty. Instead, all the synchronous code has to be run first. Line 9 gets run, line 11 gets run, all 100 million times we go through the loop. I can add a 0 to it if you would like to see that. We'll go 1 billion times and I'll run it every 100 million. This is going to lock up the thread. Even though this thing has been waiting for this much time, it will not be able to run until the synchronous code is out of the way. So if I come back over, run it again. All right, it took my computer a little less than 1 second to run this 1 billion time loop. All that time, that 787 milliseconds, this was sitting in the queue waiting to be run because we didn't give it a time to wait. We just said, here, 0 seconds, run. But because it's in the queue, it's got to wait in line. The promise.now finishes. This finishes. We have finished our synchronous code. So the global function sync code is done. Now go to the queue. So it comes back up here. This thing has been patiently waiting, and these lines run. That is exactly how it finishes. There's our performance time, and then there are the two internal ones. Okay? So in that last example, I've cleaned everything out here. The first thing that happens is the global function gets added to the stack as a frame. The very first thing in there was that set timeout. That is going to be a message that gets put in here by the web API that has that callback that runs after 0 seconds. So this is waiting. It's ready to go. This callback is sitting here patiently waiting. Meanwhile, that frame has to run from 1 out to, we ended up going out to 1 billion times. However long that takes, and it took my computer, whatever, 3/4 of a second. This has been waiting that 0 millisecond timeout. It doesn't matter. The frame gets to finish all of its synchronous code, and then it gets popped off, and then it will go looking through the queue. Then this will get pushed on as a new frame, the callback which had our console.log in it. A brief look at the documentation. I showed you this page already before, but the event loop, meaning how the JavaScript runtime model works. If we scroll down a little way, the stack is the function call from a stack of frames, and there's a little bit of info here based on the example they've got. We're going to hop over that and go to the queue. A JavaScript runtime uses a message queue, which is a list of messages to be processed. Each message has an associated function that gets called to handle the message. So these are the callbacks that are getting put in the queue down below, and they will run when the stack is empty. At some point during the event loop, the runtime starts handling the messages on the queue. That's pretty much always going to be when the stack is empty. Starting with the oldest one. This is FIFO, so first in, first out. To do so, the message is removed from the queue, and its corresponding function is called with the message as an input parameter. Right here, as always, calling a function creates a new stack frame for that function's use. The processing of functions continues until the stack is once again empty. Then the event loop will process the next message in the queue if there is one. Let's go over to this temp2. I've got a variable here called greetings. It is a function. So this is synchronous code. Once again, we're going to have, whether we like it or not, JavaScript is going to do this. It's going to wrap this around everything. And we have one global function that's going to get thrown on the stack. This variable is going to get registered, but this is just a function that hasn't been run. So it's not on the stack. It's just a, hey, if anybody calls it, it'll be ready to be put there. Same thing here. We've got another function, that gets registered. Here it is, right? Don't run it yet because it hadn't been run. Console.log1. This is synchronous code. That'll get run immediately. Say hi. It will come up and it will, oh, okay, I've got another function to put on the stack. So we now have two functions on the stack. We have the global one, and now because say hi was called, this is going to get put on the stack. So this is the top one. The stack is LIFO, so this is the one that's getting executed. Console.log2 is going to have to wait because that's lower in the stack than this thing is. We have a set timeout. So this set timeout, right, we're simulating like an API fetch or something like that. This callback is added to the queue. So even though this is running and this has run, this has to wait until 10 milliseconds has passed. Okay, inside there we call another function. Well, we don't care about that right now. Line 12 is going to run because this is part of the queue, and this is still synchronous code that can be run. We are done with that. Now we're going to come down. Line 17 is going to run, console.log2. Meanwhile, our set timeout, so the global, this has been popped off the stack, even though this is in the queue. Now this has been popped off the stack because we've run out of code. Okay, go to the queue. This won't be ready because 10 milliseconds won't have passed. By the time 10 milliseconds has passed, it will get added to the queue. The runtime engine will say, oh, I've got something ready, so it's going to take this, put it on the stack, and it's going to call greetings arn. Okay, it's going to come up top here. Here's a function. Okay, put this on the stack. This one is on the stack too. This one is now sitting on top of it. Run this code. I have a return, nothing to do, right? This is now going to get popped off because all the synchronous code has been finished. It comes down here. This is now done. And that pops off the stack. We don't have anything else in the queue. We don't have anything else that can be added. So the program is finished. So if we come over, just to prove it to you here, I'm going to run temp2. We get 1. Okay, that's line 15. Say hi gets called. We come up to say hi. This stuff happens, okay, except this is a callback, so it's put on the queue. This is still part of the current stack, so that got run, your func1. All right, came down here, it console.logs2, that's this one. It waits 10 milliseconds. Once that's finished, it calls greetings, it passes arn, this gets added to the stack, this line runs line 3 right there, it exits, this is popped off, this is popped off, and our program is finished. Okay? We'll look at this again on the board here in a second, but the last thing I want to talk about is there is a second queue. So this is a caveat that is important to know. I've got a set timeout up at the top. Okay? It's very similar to the other one. It runs after 0 seconds. Line 5, set timers added, everything's the same here. The difference is in the middle, I've got a promise. And this thing comes with a callback as well. So make a note here. Doesn't this callback get added to the queue? The answer is yes. Okay, but promises work a little bit different. They get their own queue. Promises get their own queue called the Microtask Queue. This was added in 2015 with the advent of promises. That's one reason why it took so long to implement all that stuff for the browsers, because the runtimes, or the engines had a lot of work to do. The set timeout is going to get registered 0 seconds. This is in the queue. Okay, almost immediately the web API will put it in there. This will get run first because that's part of the initial function, the stack. Down here, this is going to get added to the queue, but it's going to get added to a different queue, the Microtask Queue. Promise.then. This is going to wait until this resolves. Well, this resolves immediately. So this is going to run, and this has higher priority than does this. So I'm going to make a note here. The Microtask Queue is higher priority than the standard callback queue. If I come over and I run our code, so this time it's going to be temp microtask, we get set timer added, we should. We get I'm run first because microtask is higher, and then this was the data that we got, promised data. And then we get I was the message in the queue, but now I'm a frame on the stack. Okay, I'll walk you through it one more time. We have a global function, gets pushed on the stack. Set timeout gets run, but this callback gets put in the queue. This runs immediately because it's synchronous code. This gets run, this gets run, this gets added to the Microtask Queue. Okay, the stack, we've got a then. This can't be run yet because this is a callback, so it's got to wait. The stack is now empty. The global functions popped off. Is there anything in the Microtask Queue is the first place it will go? There is. This is ready to go. So down here, this code runs, the then runs. Back up at the top, even though this was in there first and it was waiting 0, it is second priority, and this runs last. The I'm the message in the queue and I'm a frame on the stack is the last code that gets run. So just to wrap up, talking about the Microtask Queue there, we had the global frame, or the global function gets put on, and its code gets run. We have the set timeout that gets immediately added to the queue. So here's that message. As I mentioned, though, we have another queue, and I'll put it right below here. This doesn't quite match the micro task. This doesn't quite match the the image that we've got on MDN, but the microtask queue, that's going to get registered with the promise callback. And so as soon as this frame is done, the global function, all of its synchronous code is done, it gets popped off. Even though this is older, it goes here first because this has higher priority. This is the one that actually gets pushed on. That code gets executed synchronously, all the synchronous code. It gets popped off, and then it checks again here. Is there anything there? There's not. So then this one will finally get added. Okay, that's how it works, is in that order. And so we'll talk about the heap, and then I want to give you just a quick breakdown of what to look for. What is the heap doing over here? Because it's been sitting there doing absolutely nothing the whole time. The heap is pretty much where objects live. Objects including arrays and functions. So this is the dynamic memory. As the program is running and as things are happening, stuff is getting stored over here in the heap. This is potentially another video, another conversation to have. But remember, the stack has its own memory. They have their own scope that gets managed internally here. Primitives are in there. But if you have a variable inside, say, a function that references, I don't know, we do const arr equals an array, this is going to get stored in the frame. But this is going to get stored over here in the heap. That is why, if at any point you mess with this variable, as long as it's in scope, you're not changing this variable, you're changing this variable, and this variable is over here in the heap. So later on down the road, let's say again you have another frame that gets put up here, and you're going to change this thing. You're not changing this, you're changing that. That's why it's so important to use slice or whatever method, spread syntax, something, in order to create your stuff if you want true copies, because the heap is where all that stuff is stored. But everything that's over here, I'm going to also put in here closures are over here as well. So even if something gets popped off the stack, if something else needs to have access to it, that variable will remain over here in the heap. Main thing to remember, the heap keeps track of all the objects, of all the sort of abstract reference data, things that aren't primitives, and it is independent of the stack. So as things are getting popped off, popped on, as the queue's getting moved in and out, all of that stuff, the heap is a different thing in memory, and it's JavaScript's job, right? Unlike C, where you have to do garbage collection as a developer, JavaScript manages the heap for us. As I said a minute ago, we could spend a whole long video on the heap, on how memory is allocated, how it's accessed, all of that stuff. But in reference to the event loop, really all we need to say about it is where JavaScript objects are stored. Functions, closures, arrays, etc. It is in its own allocated memory, and the stack interacts with the stuff over there. Okay, I put an annotation earlier on in the video, but strictly speaking, the stack does not contain the functions. The functions live in the heap. The frames are references to those functions, and that's the stack's job. It is its own memory that keeps track of the current stack of functions that need to be executed, and it has that stuff we mentioned earlier, the scope, the this, etc. Okay, we'll come to the event loop here in just a second, but the Microtask Queue, that was added in 2015. That is specifically for promises, so that callbacks that are relative to promises, they need higher priority. So that was added. The regular callback queue, that's existed since 1995. That's where all the other callbacks live. Okay, so the event loop. This is a simplified version. This is how I like to think about it, as a regular JavaScript loop. Okay, it's running forever. Right? That's the web browser or Node's job, is to manage how often it runs, but it's running forever. And every time we hit one of these orange lines, that means go back and start a new iteration, or go to the next iteration of the loop. And basically these the pink lines are basically case statements. Okay? So inside of our loop, the first thing we check at the top of every iteration, are there any frames on the stack? If the answer to that is yes, execute the next synchronous line of the top frame. Okay? A couple caveats. If that happens to be a function, we have to add a new frame to the top of the stack. If it happens to be a callback, add a new message to the appropriate queue, whether it's the Microtask Queue or the callback queue. Orange line, go back up. Run the next. Is there something on the stack? Run the next synchronous line that you can. If we just ran into a function call, then that is a new frame, right? So we'll be in a new frame that's even higher up on the stack than we were a minute ago. If it was a callback, we'll just be running in the next line. You just keep doing this until you run out of lines in the stack, and then there are no more frames on the stack. We'll get to this no, go to step 2. Step 2, are there any frames in the microtask queue? If the answer to that is yes, we need to move the oldest one to the top of the stack, end iteration, go back to the top. Okay? Are there any frames? There will be, because we just added one, right? A new callback. These, again, the microtask queue are the promise-related ones, and we'll just keep iterating, right? If the answer is no to this, right, it's no to this and no to this, then we go to step 3. Are there any messages in the regular callback queue? And if the answer to that is yes, then move the oldest one to the top of the stack, end iteration. There'll be one because we just put one there, and do everything like we have been, right? Execute the next line. Is it a function? Is it a callback? When we run out of that stuff, is there anything in the microtask queue? Because there might be now from this callback. Okay, when we get done with that, is there anything in the callback queue? Because there might be, because we added a callback a little bit ago. Just keep going through this process until we have nothing to do. And then the web API, it will keep the event loop going just in case something else happens. But that right there is the event loop. It is brilliant. It is incredibly effective. I love JavaScript for this very reason. I hope that this has helped out. Use the comments to expand on what I've talked about, because you can never talk about a complicated thing like this in a single video. There's always more to be said. Use the comments for that very reason. Thanks so much for watching. I will see you in the next CS Thursday video.